Boy, this display is really. Sorry, students. This display on the right side of the room appears to be kind of dim. Hopefully, you can work off this one on the left side. Uh, all right, let's keep walking up the mountain. We're going to talk about clicking scores in exam two. Your exam two total is now up in web courses in your grades page. Let's take a look at some of the specs. The exam two clicking, I uploaded this morning at about 6 a.m., 7 a.m., something like that. And so the exam two total is also up. I computed that for, except for you guys that are on the blooper list that you messed up your PIDs. I left all that stuff in my office over the weekend. I didn't have it with me this morning. So we got your grades. You know who you are. You got your printouts. And actually, if you have your printout, you can look it up and figure out what your total is. But I'll try to update that stuff later today sometime. 192 students wrote exam two. The average was pretty nice, 76 and a half. That's a little bit above 75%. I try to get about a 70% average. And sometimes I'm a little low, and sometimes a little high. This is a little high. That's all right. A lot of you guys crushed the bonus point activities on exam two. Hey, that's fine by me. If you dip your grade above 50 out of 50 by crushing the or by crushing the bonus point activities, I love to see that. That is excellent, and you get the points. So that drove the grades a little bit higher. Now, about SSG and your exam totals. Right now, there are 187 students that have taken both exams, right? Now, those students, if they also take exam three, then we'll drop the lowest score and keep the best two. All right, so for many of you, that's going to be, if you're in the set of students that take all three exams, many of you will be dropping exam one, simply because that's the one where your nervousness is highest and your knowledge of my exam procedures is the lowest. And so frequently that's the low grade that gets dropped, but not always. All right, so, but whatever is the lowest grade, if you take three, then we'll drop it. The other students, and I guess there's probably a few in here, if you were absent for one of your exams, we don't do the makeup. We count that as a zero, and that becomes your dropped exam. So you have to be there for exam three. Now, right now, almost everybody in here has at least one exam grade, right? And 187 out of 200 something that are in this section. So that's really good. All right. Now, don't blow exam three. Crush it. And hopefully you'll feel like you have begun to crush my exams. Okay, the total of those those 100 points is 73.5%. Right? So that's just below, I mean, if I were going to give a letter grade, that would be just below 75% B. So that's pretty nice. Okay? And here's something that you can't really appreciate usually until the end of the semester when we figure out what your homework pointage is going to be going into the final exam and your participation pointage. But for many of you, it's going to be 25 or maybe 24 out of 25 for homework, and similar for participation. So even if you have something right now, exam average-wise, below 75%, with your homework and clicking together, they are the same weight as a full midterm. And if you've never gotten above 40 on a midterm, which is many of you, but if you get 49 or even 50 in homework and clicking together, that's like 49 or 50 on a midterm. All right? And that's really nice. But we won't know exactly what that score is till the end of the semester. We can estimate it for the moment, and I'll try to do that this week as well. Figure out where your participation pointage is. I got a bunch of stuff to upload and update and whatnot, but so we're on average 73.5% on exams, and then factoring in a lot of pointage. It's almost like free money, Corral High. You're looking good. Things are looking good. Okay, and if everybody gets an A, I'll give everybody an A. You earn it, you get it. No curve in business in this class. A curve is the way that penalizes the people at the top that make my standard. And I have a pretty tough standard, so if you make it, you get it. And at the same time, my exams, they're tough to ace, but yet they're tough to flunk. And so usually things filter out. Now, based on exam 1 and 2 added together, if you are a student, you know who you are, hopefully now or right after class when you look at your grades. If you are over 90%, then I'll be sending you an invitation to be a special study group leader. And right now we have over a dozen who have qualified for that. Now, I want to talk about that. Go ahead and make a note, SSG, because everybody's interested in SSG, special study groups. Bonus points if you attend. Skip the final option if you lead one. Okay? And so we're going to be sending out invitations the next day or two, and we'll start organizing and whatnot. But here's typically what I do. I send out the invitations. The students that want to be special study groups leaders, which is most of them, occasionally a few say, no, I can't fit it in. They'll respond yes, and they'll tell me when and where they want to have their special study group. Then I put a sign-ups page in web courses, and then you'll be able to click into that page if your moment arrives and there's still room to join. The groups are 6 people each. So let's say that we have 12 study groups. Let's say that everybody agrees except a couple, so we're left with 12 study groups. That means 72 students, possibly, if they all fill up, and usually they fill up, will participate and get 4 bonus points on their final exam or for the semester. Now, right now, and this is something you might want to jot down, right now, out of 187 students that took both exams, only 24 are actually below 60%. All right, so that's pretty good. And here's why I'm bringing this up. In the past, it has been my practice to allow the students with a lower exam average, typically below 60%, to sign up first. And I give them an extra 2 hours, or they get the first 2 hours of sign-up time. And then after that 2 hours expires, I open it up for everybody. And I'll do all this in web courses. And every semester when I do that, there are students that aren't in the first group that complain because they can't get in. And I'll just say ahead of time, if you can't get into a special study groups, because you missed it, you didn't get in there on time and get a spot. The spots go very fast, and if you miss it, you miss it. I wish I had spots for everybody, but I don't. We might have 72. We might have a few more than that, but not a whole lot more than that. So if you want, so my guess is that if you want to get a special study group seat, you might miss out. And if you miss out, you miss out. It doesn't harm your grade, but it will help your grade in two ways. A, you'll get 4 bonus points for attending and participating. B, having participated in SSG, your exam grade will probably go up on its own. So if your previous 2 exams were 30, you might make 35 out of 50 on exam 3. Also, we'll do another round before the final. We'll do the first round before exam 3, and the second round, a separate round, separate signups. You might get in for the round that goes during finals week right before the final. All right, and we'll organize that one separately, just like we organized the SSG sessions for exam 3. Now these 2 brainiacs to my left and my right, Caroline and Darian, both started out as SSG leaders, and good ones. And so if you get an invitation to be an SSG leader, you're not required to take it, but you're going to be helping your fellow students, and you're going to have a lot of fun too. I mean, every time, I always tell the SSG leaders, hey, send me a selfie from your groups, just so I know how it's going, if everybody made it, and, just for fun. And it's always, some of them are, we had this one guy a couple semesters ago, Jordan Fiella. Does anybody know him? He's probably still on campus. He had, and some of the other guys had some of the funniest selfies from their SSG group. It was just, I'll try to dig one up. Just hilarious, the stuff that his groups did. Anyways, memorable guys. And you'll become memorable to me as well. And these guys haven't asked me yet, but other SSG leaders recently have asked me for letters of recommendation for grad school and law school and stuff like that. Yeah, so it's not just whistling Dixie. If you can make it. If you can't, you can't. All right, questions about special study groups before we continue with heat transport. Okay, let's continue. Physics notes now. I love this picture of the fire breather. Hey, did you guys see that video of the guy that set himself on fire? I was trying to look at that, but I couldn't get it to play in my cell phone for some reason. Raise your hand if you saw that. Just one person saw it? Yeah. Yeah, I heard it was terrible. Anyway, this guy's a fire breather at, I don't know, some kind of, actually it looks, I don't know if that's outdoors or indoors. I hope it's outdoors. But this actual picture is a nice look at all 3 modes of heat transport. So let's talk about them. The first one is conduction. One method of heat transport is conduction, and that's one way to think about that is physical contact between a hot object and a cold object. Now this image here, another fire breather, is nice for that, John, because it shows, oh man, well, it'll show on the podcast and YouTube. Sorry, you can't really see that. There's a guy over here on the right side of the image, and he's holding a small, I don't know, torch or something in his right hand, and he's just blown out a blob of kerosene or whatever it is that they put in their mouth and then they spit it out. Now, the way that he ignites that is with this little job here. It's not, when it's in his mouth, of course, it's not burning. He has to spit it out, and then he ignites it by contact or conduction. from this baby, this little guy, into the cloud of droplets of kerosene that he spurts out, and then they'll start a few of them will start through conduction, and then they'll blaze and ignite the rest of the stuff. Now, a fireball like this is, I believe the technical term is conflagration. There's another technical term called deflagration and also detonation. And I think this one is conflagration. In other words, it slowly propagates outward from the center of ignition and expands rather slowly. A detonation would expand extremely fast. But this is a conflagration, ignition event. The hot object is his torch, his little hand torch, and the cooler stuff is the kerosene. It raises the temperature of the cooler object. And if it's kerosene, if you go above the ignition point, bang, it turns into a gas, a hot gas that we call a flame. Okay, so this guy is using conduction to start his fireball display. Now, a counterexample to this, to conduction, is an insulator, something that does not permit heat to propagate through contact. All right, now today's kind of a chilly day, and I noticed a few people wearing warm coats. In other words, not summer. Here's another guy coming in with a jacket on. And I see people with hats on. And yeah, I mean, the reason you put that stuff on is air is a really good insulator. Heat will not propagate very well across air, an air-filled space. And that's what a fleece or a down jacket does, is it provides a network of little teeny air spaces through which heat will not propagate. It's an insulator. Some metals are not very good conductors either. You wouldn't really call a metal an insulator, but stainless steel, some kinds of stainless steel do not conduct heat very well. In other words, some kinds of steel, if like rebar from concrete, one time, I was on a canoe trip up in northern Maine, and we found this piece of rebar from when they were doing logging up there. And we had a big campfire, and we were stuck on this island, and it had a lot of driftwood, and we didn't have a lot to do, so we became pyromaniacs for a day or two until the storm passed. And one of the things that we did was we took this rebar and we built up our campfire, with stones. It wasn't just a ring of stones, like a standard campfire. We made kind of a kiln out of stones, so it became a really hot. It was almost like a furnace in there. And we stuck the end of that rebar in there, and it got so hot it became red hot. And we took it out, and we were burning our names in these big logs and different things. And the stuff that you do on a camp out, I'm not going to show a show of hands, but I see people grinning at me like, yeah, I've done that. When I was on campouts, I'm a pyro. Yeah, stuff that you do, you wouldn't normally do at home, but when you're on a camp out, you just burn stuff. Anyway, so now if we had taken a steel, that piece of rebar was just regular steel, and so we had to use some, I don't know, we used T-shirts or leather gloves or something to hold it, and because it was too hot to handle, 6 or 7 feet away from where it was red hot, at the other end of the bar. One of the bar was red hot, and then the other end wasn't red hot, but it was still really, it would have burned our hands. Okay, so we had, but if we had a stainless steel rod, it's possible we would have been able to handle it without. But loggers don't use stainless steel rebar; they just use regular steel. So we didn't have any stainless steel, but stainless steel does have that property. By the way, I want to make one more comment to you. I looked at the number of students that have now 75 out of 100 on their exam 1 and 2 total. And if you have 75 over 100, 75 out of 100, that means on exams your average is a B if I were to give you a letter grade, right? So that's not too bad. Plus factor in your participation if you're always here, your homework if you do it faithfully. You're going to be looking good. Maybe even within striking range this very minute of getting an A for the semester. Okay, and if you get an A, if you earn one, you get one. No questions asked. Anyway, let's get back to heat transport. Convection, bulk motion. And basically, convection will happen if you have two fluids, either gases or liquids, that do not conduct heat well. So for this one, in this picture, you have this fireball up here, and here's the stream of, it's kind of got a tail to it. But it's a very hot fluid made of the combustion products of kerosene burning. Right? So all kinds of hydrocarbons there. It is HOT. But air is not a good conductor. It's surrounded by air, so it's not going to conduct heat into the air very rapidly. All right? You'll feel it, but not if it was a piece of metal. The metal would conduct the heat away. Fellas, don't talk over the top of me. All right? Because I can hear you. All right? It's distracting for me and for the people around you. And if they want to get an A, if you don't want to get an A, that's all right. But everybody else around you probably wants to get an A and have a good shot, but not by being distracted. All right. So, anyways, if you have a situation like that where you have two fluids and at least one of them doesn't conduct heat well, then the hot stuff will always be on average lighter than cool stuff. And if the two fluids, one of them is hot and it's less dense, then it will rise through buoyancy forces. And that's what a fireball is. And you can see this. That's what these things do. And eventually they'll cool off and it won't glow. It won't look like fire anymore if it cools off. But I mean, it's still that hydrocarbon gas, and the wind will disperse it and all that stuff. But for a moment at any rate, you get that fireball. And it's because of basically a blob of some shape of hot fluid that's less dense embedded in a surrounding fluid, either liquid or gas, that is less dense. And that's more dense. Okay? And because you have a blob of something that's less dense embedded in a fluid that's more dense, the less dense stuff, just like bubbles, a scuba diver, the bubbles go floating up to the surface. Same thing here. All right, so the fireball rises upward on that basis. Now, there's kind of an interesting example. I mean, this is an easy to see one. Every time you see a fire breather, those things go up in the air, and eventually they dissipate. But here's one that hasn't dissipated for many millions of years. The Yellowstone mantle plume. Go ahead and make a note of that. Yellowstone National Park is famous for geysers, and they have a lot of hot springs. It's actually the remains of a huge supervolcano, they call it, that blew its top off, enormous detonation, killing many animals in North America for thousands of miles. The dust from the two most recent detonations of the Yellowstone supervolcano reached as far, the dust fallout that comes down and coats the earth, made rock formations all the way down as far as almost to the Gulf of Mexico. So that's And all the animals that were in that area, probably 90% of them got greased. So it's a pretty bad place. But Yellowstone is thermal because there's this small plume of extra hot molten lava boiling up, or I should say convecting up from the very core, pretty close to the core of the Earth, they think, is where it starts. And it goes up thousands of kilometers through the mantle and up to the crust, and it comes out at Yellowstone. And you may not realize this, but North America, the continents of the Earth in general, are like rafts made of granite. The bedrock of the continents is a kind of a granite type rock. And it's less dense, more buoyant than the stuff that is in the seafloor of the Earth, which is a dark igneous rock called basalt and basalt type rocks. So the continents are basically floating on this basalt rock, and they're moving. And that is how, if you've ever noticed, South America, the east coast of South America has approximately the same shape as the west coast of Africa. And so North America, the Caribbean, and then back out around for South America, pretty carefully, if you look at it, it almost nests perfectly with the west coast of Africa. And we think that that's actually the case, that Africa and South America and North America and part of Europe used to be all one piece of continent that fractured apart, and then the two sides of the Atlantic gradually drifted apart. It's called continental drift. And part of that is the North American plate, they call it, the huge continental plate. It's drifting over this mantle plume. And right now the mantle plume is in the northwest corner of Wyoming. We call it Yellowstone National Park, but it used to be underneath the area of Seattle and Grand Coulee Dam, the interior of Washington State and some of Oregon, and the Snake River Valley in Idaho. All the igneous rock formations through there. If you've ever been through there, if you ever go through there, you'll see huge igneous rock formations. It's almost a desert in that part of North America. And that's all because of the western edge of the North American plate passed over this mantle plume, eons and eons ago. And the North America is still heading west. So, whoa, Yellowstone. So eventually Chicago is going to be a national park. And many millions of years from, or the land where Chicago now is going to become full of geysers and hot springs and earthquakes and stuff like that, a super volcano. Kind of cool. And eventually New York. And then it'll be off the coast of North America, but we'll be long gone by then. So anyway, the Yellowstone mantle plume, and I'll probably talk a little bit more about it maybe Thursday. It's an interesting thing to look at, because they can probe the Earth with seismographs and figure out exactly where the mantle plume is, almost what its temperature is too. Third mode of heat transport, radiation. All right, electromagnetic radiation. And hey, look at this guy. I mean, that fireball, it's shining really bright. And so that's a lot of electromagnetic radiation, visible light, being blazed off the surface of that thing anyways, and transporting out. And actually, you will feel that. You could get sunburn off this thing, possibly, if it's hot enough. All right, even though it's a cold day, you may not feel it, but if this thing was there long enough, and actually the SUN is there long enough, you're exposed to the ultraviolet radiation from the sun, and it could cause sunburn. Anyways, the energy is not carried by physical contact in the normal sense, but by the transfer of momentum and energy from photons of light. Our theory of light is that, light waves and particles of light are kind of strange bedfellows, but our theory is that light is actually a particle that behaves like a wave that behaves like a particle. And one of the easiest ways to understand radiative heat transport or radiative heat dissipation is through momentum and kinetic energy carried away by photons of light. Now, visible light carries electromagnetic radiation, or is electromagnetic radiation, and carries momentum and energy. Any other kind of electromagnetic radiation does that as well. A black body that we mentioned last week is a perfect emitter of radiation, as well as a perfect absorber of radiation. We call it black because it absorbs radiation perfectly, and it's a thermal object because it's emitting radiation perfectly, and it all depends on the temperature. We looked at some of those black body spectra last time. If the material absorbs the radiation will stir up the molecules in the material and heat it up. I want you to think to yourself and ask yourself, have I used radiative heat transport to heat anything up today? Stove? No. Microwave, yeah, a microwave. A microwave generates basically radar waves, a very specific wavelength. Do you ever notice how microwaves are always about the same proportion? Maybe bigger, but roughly in the same proportion. That's because they have wavelengths or waves of a very specific wavelength that they generate. Because only that wavelength, or that wavelength especially, stirs up the water molecules inside food. You can't cook anything in a microwave if it's dry. It's got to be hot, or at least have some water molecules that are frozen. And those frozen molecules will react to that flavor of electromagnetic radiation and eventually start heating up. It's kind of cool how it works. Skin cells will stop ultraviolet. That's how you get sunburn. And here's another thing, you can make this C2, number 3, part C, part 2 of part C. If a material does not absorb radiation, it is transparent. Let me repeat that. If a material does not absorb radiation, it's transparent. So it's not really an insulator that prevents energy from going across it or through it. It's a material that lets all the energy go through it, and it kind of ignores that energy. Now, glass is a good example. Glass will transmit. You can put your hand on the windowsill and feel your hand warm up, even if it's a really cold day out. If you were up in Alaska right now and sitting by a sunny windowsill and the heat was off, you would still get some heat from the sun. Your hand would warm up. Because a lot of the visible light, some of it gets absorbed. It's not a perfectly transparent material, but a lot of it goes through and it'll warm up your hand. That's how, here's another example, C3. Example of a system that heats up through radiative heat transport is a greenhouse. Now, we don't have greenhouses here I don't know. Has anybody here ever seen a greenhouse in Florida? Epcot. Okay, other than like Epcot, they have some on campus? Really? Yeah, here in Florida, it's up north, and even Georgia probably. Did you know it was snowing up in Georgia like 2 days ago? Unbelievable. So if you're up in Georgia, north of that, in the winter you need a greenhouse if you want to grow plants. And if you think about it, you get a warm building. A greenhouse works this way: you get light for photosynthesis, and you keep the building, above freezing if you have a good greenhouse. All right. So that's radiative heat transport to the air inside the greenhouse, and also to the plants, to the chlorophyll molecules in the plants themselves. Okay, this picture is a picture of an astronaut on the moon, and those guys need shielding from radiative heat transport because the sun deposits approximately 1,370 joules per second on every square meter of Earth that's actually facing directly toward the sun. Okay, so if you're up on the North Pole, the surface of the Earth is not really facing the sun. It's kind of facing at right angles to the sun. You have to look straight south to see the sun if you're at the North Pole. But if you're at the equator, the sun's right straight up above you. So if you have a square meter balanced on the top of your head, that square meter is going to be absorbing roughly 1,370 joules per second. Did we talk about this yet? That the unit of power or energy use per second is a watt? Did we talk about that? Go ahead and make a note of it. A watt, W-A-T-T, is the metric unit of energy use or energy dissipation, and it's equivalent to 1 joule of energy transport, 1 joule of energy dissipation per second. Okay? And so the energy transported into our atmosphere from the SUN is about 1,370 joules per second per square meter. Now, if you're out at the planet Mars, all those joules per second are scattered across a lot bigger sphere, and the amount of joules per second per square meter on the planet Mars is a lot lower, quite a bit lower, because that's about 1.5 times as far from the sun as we are. Venus, they get a little bit more than 1,370. And Venus is a hot place. Mercury, forget about it. They're getting blazed by the sun because they're so close. And here, as a side note, let me just add that spacecraft satellites and stuff, are usually protected against solar heat gain by this shiny stuff called mylar. And mylar was developed, I don't know if it was developed for the space program, but they were the first ones to really use it. It reflects a lot of solar radiation. To us, that means it looks shiny. But for a spacecraft, it's needed to deflect all that incoming radiation. If you can reflect it, it won't pass through. If you're transparent, it'll pass through and not heat you up. But almost anything is going to absorb a little bit. And even the mylar will heat up a little bit. It's not 100% reflective, but it's pretty good. And it's very light, so they like using it in the space program. Now, here's another side note. These cats up there on the moon, and even some aircraft in like the Navy and the Air Force that go at ultra high altitudes, like spy planes, they have gold-coated front visor for the astronauts, and also a gold-plated canopy surrounding the pilot in these planes that go at high altitude. For among other reasons, to defeat the photons of incoming energy from the sun. Now, here's a counterexample to that. We don't always want to defeat solar heat gain. Sometimes we want to optimize for it. This thing over here on the right, that's a That's a solar heat collector for the top of your roof, right? Raise your hand if you or your parents have one of these on your house for your hot tub or nobody. Bueller, one. No, that's not. That's her hair. I thought I can't really see somebody way back over there. Nobody. One. Okay, one. I think the house that I bought recently, I think they used to have one because there's plumbing up there on the roof. Anyways, I guess more people have it up north. Anyways, solar heat collectors, yeah, you optimize that. You want to have the most solar heat gain that you can. Now, speaking of spy planes, here's what some people call the SR-71 Blackbird, but what Sam Witwicky might say is a transformer, and one of the oldest of the transformers. And this thing is famous for a lot of things. It's one of the fastest aircraft that we know of. It's the fastest aircraft that we know of. Possibly there's other aircraft flying around right now that nobody admits to having that fly faster than that. All kinds of rumors. But this is the one we know of. It's the fastest, the SR-71 Blackbird. Spy plane. Goes to like 80,000 feet or something like that. Very fast, big engines, long distance. And it can go so, and notice that it's painted black. There's a lot of reasons for that. This was the first stealth aircraft, actually, built back in the late 1950s and used all through the 60s and 70s. I actually saw one once, I think, out in Montana, late at night. And I was watching meteor showers in middle of August, the Perseid meteor showers, every August 11th and 12th. And to see those, you have to be up after midnight to see them best. You'll see a lot of meteors coming from the constellation Perseus, and it's lovely. I mean, it's a good year, a lot of meteors going through. It's beautiful. And so I'm in grad school, right? And I'm out there on one of the soccer fields, and I brought something to lie down on, a poncho or something. And I'm lying down out there just looking up at the constellation, and all of a sudden, out of the corner of my eye, I see this little, out in Montana, you can see satellites. So I'd see satellites going north to south or south to north occasionally and east to west. But this other thing, it was going really slow across the stars. And I was watching it, and I thought, oh man, look at that. It's a flock of geese. Because it had a V shape. And it was kind of red, kind of a dullish red. And I thought to myself, oh, it's a flock of geese. And you know, geese, they fly in kind of a Y-shaped formation. And so I thought, oh, it's a flock of geese, and they're so high up that they're catching the first rays of sun. From that I can't, you know, the sun hasn't risen here, but up there, they're catching some rays from the sun. And then I thought, wait a minute, it's only 2 a.m. Nobody flies that high. No geese fly that high. Plus, a big skein of geese like that would have to be really high to be as small as that one was. So I watched it go from the northeast down to the southwest. So from Montana, I was like in the middle of Montana, and it was heading towards Kansas, I guess. And then it just went across the sky. And I thought, oh, cool, whatever that is, you know, a flock of geese. I didn't really, 2 a.m., you know, I'm not really thinking that smart or anything. But I'm there watching the meteors come down. You know, they come down every few minutes. It's a good year. And then, you know, like a couple hours later, here it comes again. It's coming from southeast back to the northwest. And I thought, oh, it's a UFO. It's not geese. It's UFO. It's a UFO. And by that time, I was awake, man, because I didn't want to get, you know, kidnapped by aliens or anything. So I'm thinking. So anyways, so when the sun came up, I went home and caught a few winks, and then later on that day, I said to my research advisor, my thesis advisor, I said, Dr. Hiscock, I saw a UFO last night. I was out watching and he's looking at me like, yeah, right, kid. You know, like I'm some kind of a maniac. And I don't know if he ever believed me what I saw, that it was a UFO, but it was flying. and it was unidentified, and it was an object, so that makes it a UFO, right? But then I was telling some of my buddies, my other grad student friends, and they said, "Oh no, man, that was probably a SR-71." I said, "How do you know that?" Well, they're training this. They had just brought it out about mothballs. You know, they retired it in the 80s in like 1990, and by 95 it was back out of mothballs. They needed it for looking at Kosovo province or something like that. And so they were training flights. And so, oh yeah, they're doing training flights. And later on, I found out that these things they fly so fast that their leading edges, the front edge of their wing, the nose, the front edge of the tail fins, they get so hot they glow red. That's how fast they're going. And so now I realize that, man, I thought I saw a UFO for the X-Files or something like that, you know? But it was just a spy plane. Not very stealthy either. Yeah.
Why did it appear so slow to you?
It was way up there. Yeah. And it wasn't that slow. I mean, it was going, you know, across the sky. It took a minute to get across the sky. But what do jets do? When you see a jet, it's way up there. If it's really small, if it's up there, it'll take a couple minutes to go across the sky, right? So it was a spy plane. Anyways, so this is a famous example, the SR-71, of a metal object heating up. So I want to go through the process or talk through the concepts of how stuff heats up. So let's talk about that now. First thing we have to do is to define a unit of energy that is traditionally used in the metric system for thermal systems, the calorie. It is defined in terms of H2O. You take a gram of liquid H2O and you go from 14.5 Celsius up to 15.5 Celsius. That'd be 287.5 to 288.5 Kelvin. And then that's the amount, a calorie is the amount of energy required to do that. Right? So that's kind of the metric system definition. Now, we've used a gram of H2O to define a kilogram. And we've used H2O itself, other thermal properties, to define the freezing point and the boiling point of Celsius and Fahrenheit. But this one defines the calorie. Now, in the metric system, a calorie is 4.184 joules. Go ahead and make a note of that. And don't worry about memorizing it. I mean, I think I've got it memorized now. But 1 calorie, in the thermal sense, 1 gram of water by 1 Kelvin, is 4.184 joules of energy. So you can work all your thermal stuff in joules, or you can, what we'll do usually is work our thermal stuff in calories. Okay, it's a metric system unit. Now, who is Joule? James Prescott Joule. I will now tell you why the energy unit is named for Mr. Joule, James Prescott Joule. And he used this device that's shown here with paddle wheels, kind of like a old paddle wheel steamer, and a bunch of pulleys and stuff. This is kind of a artist's conception of it. But before we do that, let me pause for a question in the back. Go ahead. Yeah. How much what? 4.184 joules for every calorie. And the guy that figured that out was James Prescott Joule. And he was an interesting guy. He never, I don't think he went to college, but he was very smart and just did a lot of physics experimentation on his own and became very famous in England. And he determined that a certain number of joules of potential energy as measured by a change in position here, delta y. So, 1 meter of delta y for 1 kilogram. So if this brass colored cylinder was 1 kilogram and it dropped 1 meter, then that would be 9.8 joules of potential energy. And if it's dropping and it hits the floor 1 meter down, then all that kinetic energy goes into these paddles. All right? But it doesn't stop there because the paddles move water. And if the water moves fast enough, it'll warm up. So you deposit kinetic energy into the water, and then you measure the temperature change. And that is what Joule found. That so many joules, well, they didn't call them joules, they probably called them foot-pounds in his day. He was using the English system. So every foot-pound of GPE that he dumped into kinetic energy in the water corresponded to, and he probably used Fahrenheit as well. So many degrees Fahrenheit. Now, today we talk about it in terms of joules and kelvins. But, the thermal, he's the one that figured this out, this conversion here. All right? That a certain mass of water required a certain number of joules to raise it by 1 Kelvin or 1 Celsius degree. And here's the table again. And the second line of this blurb sheet here tells you that the calories that we measure for thermal activity, 4.184 joules, 1,000 of those are what a dietitian or nutritionist would call a food calorie. Okay, a food calorie is 1,000 of these little jobs. All right. In a chemistry department, they would say a food calorie is a kcal. Little k meaning 1,000, and then cal meaning a calorie. Right? But I don't use chemistry terms. We'll just call it a food calorie and a regular calorie. And there's 1,000 regulars in a food calorie. Now, that's some of the basic concepts for heating stuff up. But let's actually talk about thermal equilibrium and how you break thermal equilibrium, how you reach thermal equilibrium. If they start out at 2 different temperatures, the objects are not in thermal equilibrium. So for instance, in this diagram down here, if substance X is at a lower temperature than substance Y, then energy will flow out of Y, the hot one, into the cool one. That is the direction that heat energy will flow. Heat transport, especially heat conduction, flows in this way. All right? If you have, this also works for thermal radiation as well. And convection only happens if you have, if you're out of thermal equilibrium. There will be no convection if everything is the same temperature. And radiation could be in thermal equilibrium or out of thermal equilibrium as well. But conduction is the easiest way to look at it. So here's a big red arrow that represents the energy going out of Y and into X. All right? And you can think of it as faster molecules that tend to migrate over to X more rapidly than the stuff goes from X into Y. So sketch a little teeny arrow down here in the direction of X over to Y. Now this is a conceptual diagram. It doesn't indicate the velocities, but it does indicate like an average. So you'll have a small amount of kinetic energy because the stuff from X, I mean, if these are 2 gases or two fluids in general, the stuff from X will eventually mix over with Y, but the energy of Y, it will mix over with X, and on average, it'll bring more kinetic energy because it's originally at a hotter temperature. Now, eventually, the temperature of the two objects or the two blobs of fluid will become equal. And then your kinetic energy swapping is the same left and right. From T to X, from X to, excuse me, from Y to X, from X to Y, it's the same if they're at the same temperature. And why is that? Because the average kinetic energy is the same in the two objects if they're at the same temperature. Because remember, the temperature is precisely proportional to the average kinetic energy. So if the temperatures are equal, the average kinetic energies are equal. So if the average kinetic energies are being traded left and right, and if they're both equal, if they're being traded, things are circulating around and conducting, but they're not heating anything up anymore. And that's what we call thermal equilibrium. So when those two temperatures get to be equal, things are still zipping around. Molecules are doing what they do. If it's a fluid, they'll mix. If it's two solids, they won't mix, but they'll gradually become the same temperature and reach equilibrium. And it's when you go from equilibrium to a higher or lower temperature that you have to factor in the specific thermal properties of the material that you're working with. For instance, it takes 1 calorie to raise a gram of water, liquid water, by 1 Kelvin. All right, so make a side note of that. It takes 1 calorie to raise 1 gram of water, little teeny drop of water, by 1 Kelvin. If you have the same mass of ice, so it'll be a little smaller, because ice is less dense, so a little bit smaller, 1 gram of H2O ice, guess how much it takes to heat that up? If you're below the freezing point, it takes about half a calorie. Copper, any kind of metal, usually is very easy to heat up, so it doesn't take much energy to raise a gram of copper by 1 Kelvin. And so let's talk about that. And that property has a name. It's called the specific heat, and it's basically a numerical rating of how easy it is to heat up a gram of a certain substance. All right, so liquid water, the specific heat is equal to 1. So 1 calorie from sunlight or any other heat transport method is going to raise the temperature by 1 Kelvin. All right, and so we say that for liquid water, C, and by the way, the customary symbol for specific heat is lowercase c. Don't confuse it with the speed of light. That uses the same symbol. From the context, you'll be able to spot it. And you might want to get your clickers out because we're going to do a workout here in just a few minutes. Now, that's for liquid water. Solid water, in other words, water ice, H2O ice, specific heat is equal to 0.5 calories per gram per Kelvin. So every gram you have, if you want to raise it by 1 Kelvin, Maria, it takes 0.5 calories to do it if you're working with ice. If you're working with liquid water, you're above the melting point and everything, so there's no phase transition to worry about. If you're above the melting point, you got a gram of water, you want to raise it by 1 Kelvin, it takes 1 calorie exactly. Right? And now, here's something that is important for us. The difference between the liquid phase of H2O and the solid phase, in other words, water and ice. Okay? if you have something that is a liquid, its average kinetic energy or temperature is going to be above, or the temperature is going to be above 273. If it's solid, it's going to be below that, right? Below 273 Kelvin, crystalline bonds form. You form water crystals. It starts to become a solid. And these intermolecular bonds require energy. So we think of that as stored energy. If it's ice, it's stored energy. If you're melting it, you have to drop that energy in to break it apart. So you're working some elbow grease energy, pulling stuff apart, and versus stored energy. So you're trying to drag stored energy out of it. Okay? Or internal energy, they call that. So other substances, like, for instance, copper, you can have solid copper, and you can melt it, and it'll become molten or liquid copper. Gold is pretty easy to melt. Copper is harder. What's really hard to melt? Aluminum is hard to melt. Okay, and some steels are really hard to melt. But gold's pretty easy. Lead is really easy to melt. That's a metal, metallic lead. So if every substance is going to have a different melting point and different boiling point. And make a side note to yourself. Similar concepts apply for the transition from liquid to gas. From liquid water to water vapor, steam. Okay, but every substance is going to have different so the boiling point and the freezing, or the melting point of copper is different from the boiling point and the melting point of gold, and that's different from aluminum, and that's different from lead, and on, even for other complex molecules. Question up front. Okay. All right. Now, these concepts that we've outlined here, those are nice. Those are English sentences, and I've been doing a lot of blabbing. But here's an equation that encodes all of that. Go ahead and write this equation down. This is the heat up equation, heat up or cool down equation. Now, the amount of energy, the customary symbol, if you're working in thermal activity, heat activity, the symbol for the energy is not E or GPE or KE, it's Q. And that's just so we know that we're talking about heat energy. Now, MC delta T, that's the right side. M, as you can imagine, stands for how much you have. C, specific heat. That encodes what have you got? Do you have gold or do you have copper? Do you have solid water or do you have liquid water? Do you have a gas? Even gases have a specific heat under various conditions. And then the next thing you want to know is, how much do you want to heat it up? Or how much do you want to extract? How much do you want to cool it down? If you have hot water and you extract energy from it, its temperature will go down. And if you extract enough energy from the liquid water, it'll freeze. It'll form ice crystals. Okay, and that's how we get snow and ice. All right, so these are the things that, so here's your big question. How big is your heat up or cool down? All right. So jot this down. This is kind of the conceptual look or conceptual view of the heat up, cool down equation. MC delta T. M is the mass, C is the specific heat, delta T is the change in the temperature. And my wonderful students, in this calculation, delta T must be done in kelvins. All right, and I'm always going to be doing kelvins. Okay, I think sometimes the textbook has Celsius in there, but a Celsius, a delta T Celsius-wise is the same as a delta T Kelvin-wise because the degree sizes are the same. All right, let's do an example. And if you have your clickers ready, we'll do an example calculation if we don't run out of time. So let's melt a small piece of ice, 10 grams. All right. Now, I'm going to work in grams, calories, and kelvins. Make a note of that. Usually I'll be working in grams, kelvins, and calories. We don't have to. We can work in kilograms, in joules, and there are people that do that. But we're going to work grams, kelvins, and calories. All right, so let's say that the initial temperature of this 10-gram chunk of ice is 266. All right, and the final temperature, I want to warm it up so that it's 275. Now, that's just above the freezing point, so this is going to be cold and nice. So it's a hot day. You have a chunk of ice that's 266, still frozen, and you want it to be 2 degrees Celsius or 275 Kelvin, cold and nice. All right, now let's look at what we've got to do. The first thing that we've got to do is heat up the ice to the melting point. All right, so let's do that. Q1 equals mc delta T. All right, now here's the stuff that you need to put in here. We're going to use the heat up, cool down equation. All right, we're heating it up. My delta T is 7. That's the amount of kelvins from the initial to the melting point. What, 275, 276, 266? 266 to 273 is... No, that's my final temperature. That's my... You gotta follow me. Listen to what I'm saying. To get from the initial to the melting point, 273, it's 7 Kelvin. All right? Because something special happens at the melting point. So first phase of this process, heat it up to the melting point. All right? So for us, and here's the specific heat. It's solid water, 0.50 calories per gram Kelvin. And we've got 10 grams.
Will we just put the Nova part, the 0.50 calories per gram?
This?
Yeah.
Yeah, because we listed it in the notes a few minutes ago. On a test, I'll give you a table of specific heats and stuff. Don't worry about that. Yeah. Boiling points and, melting points and all that stuff. All right, so here's Q equals mc delta T. Now, if you multiply 10 times 0.5, 10 times 0.5 is 5. 5 times 7 is 30. Okay, so this is 35 calories over here. All right, so make a note, 35 calories for this baby. All right. Now, the second thing that we do on the other side of the boiling point, on the other side of the melting point, we go from 273, as soon as it's all melted, we go from 273 up to 275. That's my final temperature. Now, that's only 2 kelvins. So here's my calculation here. All right? But it's all melted now, so I have a different specific heat. All right? And Brittany, we're going to be doing a lot of water, H2O ice, H2O liquid, so 1 and 0.5. If we use copper or something, you can do all this with copper or gold or anything. I'll give you a listing of the specific heat, so don't worry about that. All right, so this is an easy one too. 10 times 1 is 10, times 2 is 20. So this one, the average over here is, or the amount of heat energy required to raise 10 grams of liquid water by 2 Kelvin is 20 calories. All right, so far so good. Now here's the other part, and I want you to take notes very carefully. The change of phase from solid phase to liquid phase also requires energy as well. Every gram of H2O ice at 273 requires an extra 80 calories to break up all those crystal bonds. So you're, punching away and busting up, bing, bang, all those crystalline bonds until you get a gram of liquid. And it takes 80 calories of energy to do that. But the liquid will still be at 273. So the process goes like this. The temperature will increase to 273, and then you keep the burner hot, Alexa. Or no, it's Alexa, right? Alex. You keep the burner going, but it doesn't for a few minutes it doesn't go above 273 Kelvin because everything's melting. And then once everything's melted, then it'll start to rise again. Right? So 80 calorie, and we've got 10 grams. So that means a total of 800 calories just to melt this stuff. So you can see heating it up by a few Kelvin is not that grievous for ice or for water. But melting it, oh baby, that's a lot. That's quite a bit. You're breaking up all those crystal bonds. So the total energy budget, so make a note of this, you guys. Total energy budget, 35 calories plus 800 plus 200 plus 20, total of 855. Now, thou art my wonderful students, but because it is 11:50, time to dismiss, let me just skip to this one. I'll give you a couple really cinchy heat, melt, heat, and other thermal questions for homework 13. And then Thursday we'll really crush it. You're dismissed. Yeah, I don't have them today either. I forgot them in my office. I forgot all my stuff in my office.
That was my question.
Yeah, okay. But your grade is up, right? I mean, your
Yeah, my
score is
grade's
up. Yeah.
Yeah.
I actually had a question about my test as well.